Let's talk about quantum information theory. So this time we're gonna expand a little bit more on what we were talking about last time. Last time it was more about quantum computing. We introduced what is a quantum system, its state, its evolution, and how can we apply some quantum logic gates to do some kind of calculations. And we also have seen how can we do the super dense coding. So this time we're gonna talk about it more from mathematical point of view, and more about how we can have states and how can we also manipulate them. So first of all, let's recap from the last time. We had a system with some kind of state. The state was a vector 0, 1, or some kind of superposition of 0 and 1, linear combination. And then we had also composite systems where we had some single systems and then tensor product between them. And we also had entangled states where if we measure one state, we already know another state. So yes, now this all applies only for closed systems because we only consider one possible quantum state. But what if we have some kind of combination with probabilities between the states? That means that we also include environment, not only internal system. So we can call those states that we had before pure states. We don't have any probabilities between, it's only one state. So what if you have ensemble of pure states? For example, we have probability 1/2 of having 1, probability 1/4 of having 0, and probability 1/4 of having minus state. Then we can combine those and produce another state that's gonna be called mixed state. What we do, we basically do the outer product of each vector and then do linear combination with probabilities, as you can see in this example. And this way our state is now represented as a matrix. So sometimes it's called density matrix. Actually, most of the time it's called density matrix, but in this tutorial we're gonna just call it a state. So if we have a state, then it's in matrix form. If it's pure state, then it could be written in a vector form. So yeah, now we have single system. For single system, the system is basically Hilbert space. Hilbert space, the letter H, like this one, it's nothing more than just a complex vector space and having inner product. Of course, it also has natural norm that we're gonna define later. And the state is the matrix that lives on our Hilbert space. Or to be more precise, it should be a PSD operator. PSD matrix means that it's positive semi-definite. What does it mean? Its eigenvalues all are non-negative, 0 or more than 0. And yeah, and the matrix is Hermitian. We're gonna talk about it. And trace is 1. And for evolution, the last time we just applied the matrix U. This time we have to apply the matrix from both sides, because as you can see in this example with pure state, we have the vector from both sides, so we have to apply also the matrix from both sides. But now let's talk about in general some linear algebra. So we have Hermitian. Hermitian could be like a operation that we do on matrix. So we have some kind of matrix and we have Hermitian of that matrix. We assign a dagger for it. So if we have dagger, it means it's Hermitian. What we do, it's like just having a transpose and then making the complex conjugates on these sides. As you can see, it was here I, and now it became minus I. Here it was 2 plus 3i, and here it's 2 minus 3i. so complex conjugate. So yeah, for real numbers, it's just the transpose. Now, if we call a matrix Hermitian, that means that the Hermitian of a matrix is the same matrix. So matrix A is Hermitian if its Hermitian is itself. So for example, 3i minus I 5. As you can see, if we make a transpose, it's the same matrix. Transpose and complex conjugate, it's the same matrix. And yeah, about Hermitian matrices, their eigenvalues are always all real. You'll never get a complex eigenvalue. That's good. We don't want complex eigenvalues. It's easier to calculate things. Now about the products. We didn't talk much about that last time, but we have an inner product and outer product. Inner product is basically like a basic dot product, only it matters because we have the complex numbers. So we need to also complex conjugates. And then we make this called bra vector, and this is ket vector. So for bra vector we need complex conjugates, and then we multiply. So this thing times this thing times this thing, we add them together and we get the value. So inner product is value, outer product is the matrix. So for outer product we do the same thing but on the opposite sides. So now we're gonna have to basically have a square matrix where we multiply each of those with each of the other vector entries. So this time we get a matrix like this. And it should make sense because now we got just the same thing on the left side. So now we got this kind of state. No, it's not a state. We just got an outer product. Now the norm that we mentioned, the norm would be square root of the inner product with itself. So, yep, basically just squaring and adding numbers. So normal vector we will have inner product 1, and if we have orthogonal vectors, then inner product between them will be 0. And if it's the same, it's 1. If it's different, then it's 0. So and if it's like something completely different, then we're just like picking a coefficient. You can imagine this as a projection. If we have 1, ket bra 1, and ket some kind of vector, and just picking coefficient from here. So for example, we're picking coefficient next to a 1, which is minus 1 over square root of 2. So that's our inner product. The same goes here. We're just picking, this time we are picking weighted sum, because plus is 0 plus 1 with 1 over square root of 2. So this time we're doing the same with both of these values and we get another number. And the outer product, if it's the same thing, the pure state, also a projection. Projection is just the matrix that squared is the same matrix. And yeah, these are the operations that we do on matrices and vectors. So let's get back to our states. We're working again on a single system. Pure state is a state that we can write in this form: ket and bra. And yeah, this is an example. We had a vector 0, which was expressed as 1, 0. And if we want to write it in the matrix form as a density matrix, we apply these vectors, multiply them, and we get this kind of matrix. So this is our state. And then we want to apply, for example, x gate to it. So we're gonna have x gate here, then we have a Hermitian of x gate here. We add those together, and as you can see, we apply x to this vector, we apply Hermitian x to this vector, so we get 1, 1, as we should have, because it was the definition of x gate. So the pure state will have rank 1, as you can see it's only one number here, and here zeros. And also pure state always will have eigenvalues 1 and 0, and it's gonna be, as mentioned before, projection, so rho squared is rho. Now mixed state, so it's a classic, also called classical state. Mixed state, by definition, as we've seen before, is just a combination of pure states. So, or in other words, if we have matrix that is a mixed state, we can expand it. Expand by eigendecomposition. So any Hermitian we can expand in eigendecomposition, which means we can find eigenvalues, and then we can find eigenvectors correspondingly that suits us, normalized vectors, and we combine everything and we have expansion. So yeah, these are the eigenvalues, and then these are the eigenvectors. So for example, we can have a state that is 3/4 and then of this vector, and then 1/4 this vector. This eigenvector, this eigenvector, this is eigenvalue, this is eigenvalue. Here, another vector, matrix. And then we have here eigenvalue, one eigenvalue, 1/2, right? It's a diagonal matrix, right? Diagonal matrix, 1/2, 1/2. So these are the eigenvalues on the diagonal. So 1/2, 1/2, and then we have eigenvectors, 0 and 1, and we make this decomposition. So this is maximally mixed state because it's the identity matrix. Here we have dyadic decomposition. It's not the same. As you can see, here is 0 and 1 combined. It's not the same vector. So this is not eigendecomposition. If it was eigendecomposition, we wouldn't have these two things. It would be only zeros and only ones. But if we want to do the eigendecomposition, then we have to find eigenvalues. So this is a pure state. We can check it by squaring it. We square it and we get the same state. So it's pure state, that means eigenvalues are 0 and 1. So for 0 we have this eigenvector, for 1 we have this eigenvector, and then we make this outer product, and we can expand our state into this form. And as you can see, we got the same thing again, but now we know what are the vectors that combine that state. So this is the eigendecomposition, finding eigenvalues and finding eigenvectors and expanding. And yeah, because of this expansion, we can consider eigenvalues as probabilities and eigenvectors as our pure states. In this way, it works the same as we intended. Our mixed state is just a combination of pure states with their probabilities. Now, it's also sometimes inconvenient to use Bloch sphere. Not drawing it, it's really popular. You can find diagrams everywhere. But from mathematical side, it's just having any state being able to expand in this form using x, y, and z gates. So we can express any state in three real numbers. No, not necessarily real numbers. Complex numbers could be. For example, this state could be expressed in this form. So yes, that's in general how states work in our new way of expressing them with matrices. So this is how mixed state work and how density matrices work. So this is the single system, the most basic example. Now what happens if we have composite system? So I'm gonna erase these. What happens if we have composite system? This one. yes, if we have composite system, then we combining with tensor product two Hilbert spaces or more Hilbert spaces. So we tensoring Hilbert spaces, and our state we're also gonna be BSD on tensored Hilbert spaces. But it's again, it's again a matrix that is Hermitian, and its eigenvalues are all real. Yeah, by definition, not by definition, but it's a property for Hermitians. And also eigenvalues are all positive, not negative, could be 0. The trace is 1. That's why we can say that the eigenvalues are probabilities, because they sum up to 1. And now we have product state. Product state is the one that we can write as a tensor product of other two states on single systems. So for example, 0, 0. It's product state because we can write it as 0, 0 tensor 0, 0. This is also a product state because we can write it as this state tensor this state. This is on one system, this is on one system. We combine them, we have a composite system, and we have the product state. So this is the most simple example that you can basically use for any classical system. Now we have separable states. Separable states, or otherwise called classically correlated, is also a classical example. It doesn't have any fancy quantum properties. It's just having linear combination of those product states. So yeah, it's just mixed state. So we just have probabilities and product states. So we can easily manipulate. If we have some kind of property on product state, we can just apply it for a separable state that is not a product state just by linearity. We will see that later. And we also have entangled state, that is quantum correlated state. So yeah, by definition, it's just neither of them, not separable. In simple terms, not separable. That means that we cannot write it as a tensor product of our two states, nor linear combination of tensor products, convex combination. Yeah, there's a simple example like this. We have pure state that is entangled, and yeah, this is how it looks. As you can see, there's no way to separate these because we have 0, 0 here, and here it's 1. So there's no way to separate these. And the same here goes here, 0, 0 here, and 1 here. So there's no way to separate. And yeah, and then we have standard, we're not gonna use basic maximal entangled states. We're just gonna talk about standard maximal entangled states that are of this form. We're not gonna have many more examples. They have some properties. We can talk about it maybe in another video. So here we have the maximal entangled state. And as you can see, it's 0, 0, 1, 1. As for definition, x, x. So if it was like, I don't know, 0, 0, 0, 1, 1, 1, could be maybe not only 0 or 1, could be 2. Then it would be 0, 0, 0, 1, 1, 1, 2, 2, 2. If the dimension of our Hilbert space is 3. And yeah, these are the basics about our composite system states. Now, what can we do with that? What can we do is, firstly, we can have reduced state. That means if we have composite system, we can somehow extract one of the systems. Now, what's the catch? The catch is that we lose information. So if we if the state is product state, then it's all okay. We just extract one of the states, one of the system states. But if it's separable or entangled, which means correlated, then we lose information because of that correlation. We separate states and we lose the correlation. So it's not going to be the same. We cannot recombine again the same state. So here we have some kind of state, right? Raw AB, and by definition, our reduced state, for example, on system A, is gonna be partial transpose on B, partial transpose B on our state. By definition, it's like this. So applying vector B on the B system. Vector B is just basis state, and then we have some of these. For example, we have vector like this matrix. This is entangled state. You can write it as this by our eigendecomposition. This is our dyadic decomposition. We can use dyadic decomposition for our definition. So basis states of our system B is 0 and 1. So we have 0 applied and then 1 applied, and we have a sum of that. So this identity matrix, and this is 0 vector. It's, yeah, basically identity means that we don't do anything. So here you can see that identity just gone, and this vector is just applying this vector to the second system. So as you can see, 0 stays the same, and here 0 gets another 0 on the left. Same goes here. The first one stays the same, the second one gets a 0 on his right side. And yeah, this way we can see that this cancels out. This is 1, so it just cancels out. This is 0, so we cancel out the whole term. And as you can see here, we actually use the linear property, because this state is separable, but it's not product state. But because it's separable, we can write it as a sum of product states. So we use linearity, and then we can, well, it's not really product states, but we still can use linearity and just calculate transposes of these single terms. And yeah, we get that everything cancels out, and it's left only 0, 0 and 1, 1. We add those together and we get identity. So as you can see, we had entangled state. From entangled state, we just wanted to extract one system state, and we got identity, which is maximally mixed state. So if we recombine that, we just get a product state that is not correlated at all. Yeah, so we lose information. Now for the product state, and separable in general, as you've seen, we have, yeah, we can just basically use transpose on one matrix. So but it's just a general definition, because if we are talking about quantum states, quantum state transpose will always be 1, as we've seen by definition, right? Quantum state is a PSD operator, and also a trace should be 1. So this trace will always be 1. So as you can see, if we want to get reduced state on the first system, A system, and we just trace out B system, and we B matrix, and it's just the first matrix, as we were intending. And here's an example. We have this thing, we want to trace out the B system, and its trace is always 1, so we just remove it, and that's it. We are left with A system vector, A system state, this matrix. How does it look from graphical intuition? We're just basically grouping into 2 by 2. We're just grouping our matrix entries. So for example, this is our state. We want to trace out B and leave only with state on A system. So okay, first of all, this is a state as mentioned before because its trace is 1 and it is a PSD. So here we can see that we basically just choose by the first number 0 0 0 1 1 0 1 1. So we choose by 0 0 0 1 1 0 1 1, and we calculate traces on these parts, and we get this thing, and this is our state row A. We do the same here, but now it's a little bit difficult to visualize because now we're switching between the rows. We get again 0 0 0 0, then 0 0 0 0 here. Well, you can see by the colors it's again combination, but now on the second number, and we again calculate traces of these things, and we get our state row B. And as you can see, if we do the tensor product, it's not the same thing. It's gonna be the same thing only if it's a product state, as mentioned before. Only if a product state, we get by this property back to the same state. Yeah, but product state, it's nothing special. Yes, so we lose information, and we see what information basically is accessible locally for that state. For example, we have two qubits, we entangle them, we send one to another galaxy or whatever. So if we measure one of them, we only can extract information on this transpose, or not transpose, on this partial trace. We can only extract on partial trace. And we lose information because we are measuring. So again, if we want to extract information from the B system, locally accessible is only the partial trace. Yes. For example, for measurement, we're gonna see the measurement definition. Partial transpose, partial trace. What am I talking about? Okay, it's partial trace, right? Partial trace. Well, I'm not gonna record it again, so yeah, just keep it in mind. Okay. Yes, okay. Reduce state. Okay. Now we need purification. Purification. So what we do the opposite of reduction. So we have a mixed state and we want to purify it. So we're finding what was the initial state that we reduced. And we're not choosing any state, we're choosing pure state. So basically, how do we get from this that we reduced to, how do we get back to this pure state? And turns out we always can do that. With any mixed state, we can get back to some kind of pure state on the on the bigger Hilbert space. For example, here we can purify it to a bigger pure state. And yeah, if it wasn't mixed, if it was a pure state, we can just add any other pure state. We make a product, tensor product. We have a product state which is again pure. So simple as that. So we're not interested in that. We're more interested in the mixed state. And yeah, for any state we can do that. We can get some kind of pure state, of which reduced state is our state that we have right now. And this pure state of which the reduction can happen is called the purification. And we have infinitely many of those. So keep in mind that. So we're not gonna calculate infinitely many of those. We're just gonna choose one standard purification. And by definition, it's like this, right? We apply this thing, square root of our state, to the first qubit, to the first system qubit state, like this. And then we sum through all the standard basis states. So it could be just like decomposition with eigenvectors, for example. But it could be any standard basis, but usually it's gonna be just eigenvectors because we can do the eigendecomposition with that. And what does square root of matrix means? Well, we can do expansion, right? If it's Hermitian matrix, we're talking about Hermitian matrices, right? Because it's a state. So it's Hermitian. So we can expand it with eigendecomposition. So we're gonna have eigenvalues and eigenvectors. And what we're gonna do, we're just gonna get square roots of eigenvalues. And we're gonna keep eigenvectors the same. And if you do so, we get another state, which is again a state because it's it's Hermitian, as it should be. And that's gonna be our square root of our state. And then we just apply it to all the first qubits. So example, right? We have this state, this vector, this matrix. And we do eigendecomposition because it's Hermitian matrix, because it's a state, right? It's also trace one. And we do eigendecomposition, so we calculate eigenvalues, right? We have this formula, determinant, right? I'm not gonna expand on this, but we apply this formula and we calculate eigenvalues. Then for each eigenvalue, we calculate eigenvectors and we normalize them. So we're gonna have like infinitely many eigenvectors, but we choose those that are normalized. So it's gonna be only one normalized for each eigenvalue. And yeah, this way we can calculate the square root of our state. We just get square roots of our eigenvalues and keep eigenvectors the same in our eigendecomposition. Now the next thing what we do is we find the standard purification by definition. So now, as mentioned before, our standard basis could be 0 and 1, but it's really uncomfortable, really inconvenient to use that. So we're just gonna use our eigenvectors, which is again a standard basis, because by eigendecomposition means that those eigenvectors form a orthonormal basis. So yeah, so these are our basis vectors, v1 and v2. So we expand with sum and we apply our square root of our state to the first vector here, first vector here. We calculate it and we get this state. So this is our standard purification. It's a pure state, right? This is a vector, so we can just do outer product with itself if we want the matrix form. And that's our pure state. And we can check if we do the reduction on it. For example, we want to reduce to the A system. We see that we calculate partial trace and it's gonna be our initial state that we started with, right? We did eigendecomposition. This is the eigendecomposition of our state. You can see here explanation, right? Because it's pure vector, we do the outer product, so we multiply each vector with each vector from this side. But the trace, if these vectors are orthogonal, the trace is gonna be 0, right? Here you can see by trace definition, right? Trace definition is sum of all the basis states multiplied around our state, and you can see it goes to 0. So if these are orthogonal, it's always trace 0. So trace 0 also here, and we only have these two. And if it's the same state, then trace is 1. So here's trace 1, here's trace 1, and we get exactly the state that we started with. So as you can see, we get some kind of like cancelling out thing, because here these two things cancel out, right? So we just magically add them, and then we get another state that is bigger, but it's pure. And if we want to, we can again reduce it, remove these two things, and we end up again in our initial state. So we can do to the both directions. We can have some kind of mixed state. We can have any state and just do partial trace. So we reduce, right? We can reduce from composite system to one system, and we can do the opposite. We can have single system, and then we can purify it, so we can find a bigger on two systems, composite system state that could reduce back to our state. So you can do both directions. So this is the purification. We can move around our composite system, but again we're losing information, right? Okay. Yes, because of our standard purification, turns out that we can do again back the way we went. So we had system A state, have state on system AB, then we reduce it with partial trace, we get state on system on one of systems. And we can do the opposite, purify, and we have formula for standard purification, and we get again AB, but it's probably not the same. This is gonna be a pure state, so it's not the same state. But turns out if we have this pure state, then we can do again to this. Then it means that we actually can just expand this pure state in our original purification thing. So we can just decompose our pure state into this kind of standard purification thing. So yeah, now we go again this direction. So we have our pure state that could be purification of some kind of other smaller state. So we decompose it into the formula that we use for standard purification. So yeah, this is how it works. So we have, this is orthonormal basis on one of our systems, orthonormal basis on another system, and then we have some kind of real values here, positive values, and we can decompose, as we already had an example. Alright, and that leads us to our final decomposition, which is singular value decomposition. this is mostly used for operators, so it's like a general case for eigendecomposition. Again, we can imagine it as some kind of operation on m dagger m or mm dagger. So for this definition, we can just consider not just m state, but m dagger m. If we have this kind of state, it's Hermitian. This is also Hermitian. And if it's Hermitian, then we can expand it by eigendecomposition, right? So we expand it. And what do we get? We get the same thing in the middle, which means it's 1. So we can just cancel it out. And what we're left with? This thing, which is, right, it's our eigendecomposition. And here it's the same, right? We can write it, sorry, I mixed up. By our definition from here, we can expand, right? Expanding one, expanding another. And this is the explanation why it's k here and h here. Because from one expansion and another expansion, k's cancel out. And we're left with eigendecomposition. This is eigendecomposition, so this is Hermitian. Again here, we also have eigendecomposition, so this is also Hermitian. And this is eigendecomposition that is that's resulted from this cancellation. So again, we're kinda just expanding eigendecomposition from this state, mm, and then just inserting some kind of other state in the middle. And we can do that because it's always gonna be 1 here. So we're just inserting this thing in the middle, and then we just separating. We're separating again into 2 states, 2 operators. So this composition is single value decomposition. So it's very similar to eigendecomposition. We're just using 2 matrices for that. And then the middle cancels out. So yeah, so because of this, singular values are just eigenvalues of square root of m dagger m. Or m dagger, doesn't matter. Eigenvalues are the same. And yes, this is how it works. We have eigenvalue here, and this is multiplication of 2 singular values. That is why this is the squared singular value. Or singular value is square root of this eigenvalue. So yeah, this is how it works. What can we do? We can have an example. We have some kind of matrix. Yes, it's not a state, it's just random matrix, because this trace is not 1, it's not even PSD, because it's not Hermitian even. But we can still do singular value decomposition. We can do that for any matrix, any square matrix. So what do? We calculate m dagger m, we get its eigenvalues. And because we have eigenvalues, we can have singular values. We just square root of eigenvalues. And then we can have our eigenvectors. Eigenvectors, so we have this left singular vector, right singular vector, which is basically eigenvector of one multiplication, eigenvector of another multiplication, m dagger m, m dagger. So we calculate those, and we get our singular value decomposition. So it's not looking nice, even though our matrix is really simple. But we still can do it. We can do it with any matrix. So this is how it relates with the eigendecomposition. So to recap, we had some kind of state. We can any kind of state on 2 systems, for example. We can reduce it using partial trace, and then we can purify it back So we can find some kind of pure state, bigger pure state that we could back reduce, right? So we can reduce multiple things to this. Reduce to this thing. What only one of them is pure. So we can get back to the pure state which we could reduce. So we have purification, standard purification, only one standard purification, infinitely many purifications in general. And yeah, and because of that, we have a way to decompose our pure state. By this definition, we can decompose in this way. And for operators, we can also decompose with singular values, so basically the same as eigen decomposition, which was for Hermitians. So we just artificially make a Hermitian by multiplying with its Hermitian, right? We have matrix Hermitian, multiply them, we get a Hermitian matrix. So it can be expanded with eigendecomposition, and then we can insert this thing and again separate those two things. And the last thing I want to talk about when we have covered all of these things is the measurement, because now we can apply those things. So we again can measure on single system or composite systems. For single system, it's really simple. What we do, we basically have a projector. So if it's basis measurement, we have projector. It could be not basis measurement, but the main thing is that measurement should have some kind of set of outcomes, omega set, and each outcome should be mapped to some kind of PSD operator. Each outcome should produce some kind of state. So for example, we have and sum of all of those measurement matrices should be identity matrix. And probability is calculated by the trace of this measurement applied to our state. So for example, we have single system with a projector, so on the basis states. So we have two outcomes possible, 1 and 0. So our measurement with on 1 is just 1 1 matrix, measurement on 0 is 0 0 matrix. So this projector, we apply this projector to calculate for probability, because we're measuring, so we're just gonna have probability and our state will collapse. No other state will be left, only classical information. So for example, we have minus state. We can expand it with dyadic decomposition. It's not eigendecomposition. And then we can have probability by calculating the trace of this product. So trace of this product is trace of this thing. Again, trace is linear, so we can just pick all those terms separately with our dyadic decomposition, and then just calculate traces of each one of them. So here the trace will be 0, because here 0 and 1, as mentioned before, inner product is 0 because we are orthogonal. It's gonna be the same thing with all of these except for 1 1. And for 1 1, the trace will be 1. And yes, this way we get our probability 1/2. But it means that it doesn't necessarily have to be ones and zeros. We can actually measure on any other basis. So then in literature you can see, when reading you can see mentioning on z basis. So 1 and 0 is just a z basis, a z operator eigenvectors, 1 and 0. So we can have any other basis, for example, Hadamard basis. So this would be Hadamard basis, if I'm not mistaken. And this way we can have, for example, the same state, minus state. And we again can measure and calculate probability of 1. But this time it's gonna be 1. Probability is 1. So if we're measuring on this basis, minus and plus, we're always gonna get 1. If we're measuring on 1 and 0, we're gonna have probability 1/2 measuring one or another. So yeah, this way we can actually measure on different bases. But we can also have not even a projective measurement. For example, this one, it's not projective, right? We have 2/3 for each of those things. And but it's still, some of these is still a identity matrix. So it's still a measurement. Now for composite systems, it's a little bit more complex. For composite systems, we can measure just one subsystem. So like this. Well, what does it mean? It means just like on the other system, it's going to be identity. So it doesn't change anything. So if it's 0, star means any just star, one outcome, right? And it's not changing anything. And for this measurement, we have 2 examples. We have separable, correlated, classically correlated system, and separable state, which is again convex combination of products. So we write it as a convex combination of products, and then we calculate, for example, what is the probability that we measure 0. So we apply this matrix now, this measurement operator, and again calculate trace, and we get what? Again 1/2. But now, since we measured only one of the systems, only one of the subsystems, we can see that the B system still has a quantum state, and we can find that state using this formula. We started with examples, right? This is composite system definitions. So for composite system, we just combining with this product 2 measurements, and we apply those to the state, and we get again trace is probability, but now we have this definition without question marks. Yeah, this definition, where we just use, as mentioned before, partial trace, which kind of reduces our information, but we get what we can from our local point. So locally we can access this information, which is basically just a measurement. So this is our trace, partial trace, and we also normalize by dividing by probability. So again, we apply this measurement to our state, and we calculate trace and get probability that on the first system we measure 0. What the second system get? The second system gets this state. So we do a normalization by dividing, and here is our partial trace on, again, measurement applied to our state, which is again 0, 0, the same thing. And the partial trace is 0, 0. These cancels out, and this is the state we are left with. So if we measure on the A subsystem, if we measure 0, then on the second system, B system, we get 0 state, and the probability for that is 1/2. We're not gonna discuss the other measurement, it's a bit too much. And another example is for entangled state. If we have entangled state, again, we can measure only on one. We can, for example, measure on one subsystem, on A, for example. If we measure on A, and so the probability to get 0, again, we apply measurement to the state, calculate its trace, we get 1/2. Then we again apply measurement to our state, calculate partial trace, and then we get what? we also normalize by dividing the probability we calculated, and we get the state. This is the state B after measuring state A. And what is the probability of us measuring 1 on the first state, on the A system? Again, measurement applied for the state, calculating trace, we get 1/2. What is the state left on the B system? The B subsystem has now partial trace on measurement applied to the state, and again normalized by dividing on the probability, and we get this thing. So this is the entangled state that was measured only on one system, on one subsystem A. And as you can see, probability is 1/2 of getting 1 and 0, as it should be by this expansion. And when we measure 1, you can see that the other one will definitely also be 0, because now we can measure this thing, and well, of course it's 0, right? Beyond the possibility. Here we again can measure, and it's also always gonna be 1. So yeah, this way we can see. Oh, it's not right. This cancels out, right? Normalization. So right. So we get 0 here and 1 here. We measured 0, got 0 on another, measured 1, got 1 on another. As it should be. Now what happens if we have joint measurement? Well, it's the same as single system, and we just measure and all the state collapse, so we only get a classical outcome. For example, we have measurement like this, on basis state, computational basis. The product state, we have some example product state, and again we calculate probabilities by applying by calculating traces. And we're not gonna go through that, but again, we can calculate probabilities with traces on measurement times our state. And it's gonna be it for today. I know it's a long tutorial, so I probably should have separated into multiple parts, but it's still only like 1/3 of the course, so I'm probably still gonna do other videos for this, of this type, to just recap and cover all the materials I need for the exam. I'm gonna also upload to the description, you will see some links to these boards. And that's it for today. Thanks for watching.